Welcome to Topic 10 Honors Unit Advanced Exponential Models. Here we're going to be exploring Newton's Law of Cooling and Logistic Growth. Newton's Law of Cooling models what happens when something cools down. Think about if you were to bake cookies. When you take them out of the oven, your cookies are hot. They're the temperature of the oven, say 350 degrees. And you have to wait for some period of time before they get cool enough to eat. The cookies will cool at an exponential rate, but at some point the cooling is going to slow down until they reach the temperature of the room. So when we look at Newton's law of cooling, the temperature U of a heated object at a given time t can be modeled by the following function. U of t is equal to t plus u of 0 minus t times e to the kt, where k is less than 0. So t represents the constant temperature of the surrounding medium. Say the temperature of your kitchen. U of 0 is the initial temperature of the heated object, like in our cookies, 350 degrees. And K is a negative constant because the temperature is decreasing. Example 1, an object is heated to 100 degrees C and cooled in a room with air temperature of 30 degrees C. If the temperature of the object is 80 degrees C after 5 minutes, when will the temperature be 50 degrees C? So let's list what we know. The initial temperature, U of 0, is 100 degrees C. The air temperature of the room, the surrounding medium, is 30 degrees C. If the temperature of the object is 80 degrees C after 5 minutes, that means that U of 5 is equal to 80 degrees C. We're being asked to find when will U of t equal 50 degrees C. So in order for us to answer this, we're going to have to take the given information and calculate what our k is equal to. So I'm going to plug my values in so that I can find k, and we'll say that u of 5 is equal to t plus u of 0 minus t e to the k times 5. I'll replace u of 5 with 80, t with 30, u of 0 is 100, minus 30, and e to the 5k. If I subtract 30, I get 50. 100 minus 30 is 70, e to the 5k. Now I'm going to have to use logarithms to isolate that k, but before I do that I need to isolate e to the 5k by dividing both sides by 70, and I wind up with 5/7 is equal to e to the 5k. Now if I take the natural log of both sides, that means that the natural log of 5/7 is equal to 5k, or k is equal to the natural log of 5/7 over 5, which is approximately equal to negative 0.067294. Usually I like to keep k in terms of a natural log, but that's kind of an awkward number to keep writing, so I'm going to go ahead and use a decimal approximation, but I want to go out a lot of decimal places so that I don't have round off error. So now that I know k, I can figure out when will u of t equal 50 degrees. So I'm going to replace u of t with 50. My room temperature is still 30. My initial temperature is still 100 minus 30, and this is going to become e to the negative 0.067294 times t. I will subtract 30 from both sides and divide by 70, and I wind up with 2/7 is equal to e to the negative 0.067294 t. I'll take the natural log of both sides, and I'm going to get that negative 0.067294 t is equal to the natural log of 2/7, or t is equal to the natural log of 2/7 divided by negative 0.067294, and t is approximately equal to 18.6 minutes. Now we're going to talk about logistic growth. Logistic growth models a growth that for a period of time grows exponentially but gradually has to reach a maximum value, which we call the carrying capacity. Right here is the general equation for logistic growth. The value in the numerator is the carrying capacity, and B is a constant determined by the rate of growth. Example 2. Fruit flies population in a bottle after T days is given by this logistic model. State the carrying capacity and the growth rate. Well, the numerator is always the carrying capacity, so the carrying capacity is 230 flies. And because B represents the growth rate, B is equal to negative 0.37. So we're going to say that the growth rate is 37%. Part B, determine the initial population. P of 0 is going to be 230 divided by 1 plus 56.5 times e to the negative 0.37 times 0. Well, remember that e to the 0 is equal to 1, so this is 230 divided by 1 plus 56.5, and this is equal to 4 flies. Part C, what is the population after 5 days? So now I'm going to evaluate P of 5, and that's 230 over 1 plus 56.5 times e to the negative 0.37 times 5. And if I put that into my calculator, I get approximately 23 flies after 5 days. And finally, part D, how long will it take the population to reach 180? So now I am going to replace P of T with 180. I'll rewrite my equation, leaving T as a variable. And now I need to solve for T. Now if I multiply both sides by the denominator and divide both sides by 180, I'm going to get that 1 plus 56.5 e to the negative 0.37t is equal to 230 over 180. And then if I subtract 1 from both sides, I'm going to get 56.5 e to the negative 0.37t is equal to 230 divided by 180 minus 1 is equal to 0.2777. If I divide both sides by 56.5, I get e to the negative 0.37t is equal to 0.00491164. If I take the natural log of both sides, the left side becomes negative 0.37t, and that's equal to the natural log of 0.00491164. And if I divide both sides by negative 0.37, I get approximately 14.4 days. That's all for now. Thanks for watching.